3, 2, 1, we're starting. Today's lesson is over parallel and perpendicular lines and the relationships between their slopes and therefore their equations. Let's get started. The graph here shows two parallel lines. You can see that they don't ever intersect. They have the same distance in between them. We're going to call these F and G. And let's explore what we notice about the equations of those. If we write the equation of line F in slope-intercept, let's go ahead and determine that. And slope-intercept is y equals mx plus b. So let's pick 2 points here and compute our rise over run. So it looks like we go up 1 and over 2. And our y-intercept is at positive 3. So for line F, we are intersecting at y equals 3, and we are going up 1 over 2, up 1 over 2. Every time I go up 1 over 2, I land on the line again. So our equation would be y equals that rise over run. That's our slope. That always goes with our x, and then our y-intercept next to it. Now let's do the same thing when we find the equation for line G in slope-intercept form. So this intercept looks like to be at negative 1. Let's go ahead and label those. At negative 1, and if we determine the slope and pick a few other points that land nicely, we notice it goes up 1 over 2 again, up 1 over 2, up 1 over 2, so it's a rise and run of 1 over 2 again. But our y-intercept is different. So rise over run, this is for G. In fact, maybe we should have been better about this and called this f of x and g of x. That's the idea, right? And then our, nope, that was a negative 1. So we'll just write it like that. Okay, so we're looking at g of x is 1/2 x minus 1. So if you look at the two lines, we can tell here in the graph they're parallel. And if we look at their two equations, we can see that their y-intercepts are different, but the slopes are the same. And because they have that exact same steepness, they started at different points, but they have the exact same steepness. That's what causes them to be parallel, okay, to be at the exact same, angle or steepness all the way through and never intersect. So if we compare these, we can say that lines F and G, if we notice their equations, they have the same slope. That's the biggie here, but different y-intercepts. Okay. And that brings us to one of the big key features of parallel lines. So parallel lines on a coordinate plane are lines that are the same or equal distance from each other at all points. So it's always the same distance away from each other. So same or equal. Or equal distance from each other at all points. And they have the same slope. I'm using a pen. Okay. Parallel lines will never intersect. So let's go ahead and write that in. Same, so you can see that. Okay, so they always have the same slope. They're always the same or equal distance. Okay, and they'll never intersect each other. Okay. But the big things are what causes all of this to happen when we look at the equations. The key feature there is right over here. We can see that they have the same slope but different y-intercepts. So find the slope of the line parallel to the given equations. If I'm given a line and I want to confirm or guarantee that it's going to be parallel to it, we now know that that basically means it needs to have the same slope as the original. So for number 1, the first thing that I want to do is identify the slope of this current line. Okay, so remember the slope is always attached to x. In this particular case, our slope is 5 over 2. If I want my line to be parallel, then my line also has to have a slope of 5 over 2. Okay, and then as long as my line has the same slope, then and different y-intercepts, then they'll be parallel. But if I want my line to be parallel, it has to have this slope so that it will be parallel to that line. Okay, take a look at number 2. On number 2, again, find the slope of the line parallel to the given equation. Be careful here. They kind of threw a curveball at us. The x term is actually behind. It may help you to put that x term in front of the 9 and rewrite it so it's in that more traditional y equals mx plus b. But as long as you can identify where that m value is, then we're still okay. All right. So in this case, we would want our line to have a slope of -2. Take a look at number 3. Same thing. It's not quite in slope intercept form. Y is not isolated. Be careful not to jump too fast here to make some decisions until you know that it is in that y equals mx plus b where the y is completely isolated. So before I make any decisions or determinations, I do need to divide everything by 3 here and rewrite this in y equals mx plus b. Okay, so I divide everything that isolates our y, that gives us our true slope and our y-intercept, and then we can say, okay, well, if I want to be parallel to this line, then my line has to have a slope of 4/3. Okay. The most common place where we start to do parallel and perpendicular lines is creating a new equation that is parallel or, in a moment, perpendicular to another. So let's start with number 4. If you look at number 4, we are going to write an equation of a line that is parallel to this one and has a y-intercept of -8. Okay, so that one's pretty straightforward. Again, make sure this is in y-intercept, slope-intercept form, Identify your m value. Okay, this is our m, is -4, but we want ours to have a y-intercept of -8. So the slope of our line would need to match the other one, and our line would have to have that slope but this new y-intercept, so our equation would look like this. Okay. Try number 5. Remember, you may need to put it in slope-intercept first and then proceed. All right, let's see how it went on number 5. Again, this one wasn't isolated quite yet, so before we made a decision, be careful not to just grab that 2. Make sure that you have divided and isolated that y value to really be able to determine what that slope is. So now we know our slope needs to be 2/3 here. And then it says, but our equation, when we write it, needs to be parallel. So we're going to use the same slope. And it needs to cross the y-axis at 6. Well, that's just a fancy way of telling us the y-intercept. So if we know what the y-intercept is, then we know we have all the ingredients we need. Our line is going to have this slope, but it will have a y-intercept of 6 because that's where they wanted to cross the y-axis. Okay, so let's just practice maybe one more where we don't have the y-intercept and we have to find it. Let's talk about how we do that. This is something we've already learned to do. We're just going to put it into practice. If you take a look at number 6, it says a line. We want to write the equation in slope-intercept for a line parallel to y equals 1/4 x minus 9, but it passes through 8, 1. Okay, now, big things. This is already in slope-intercept. That's good news. That means that 1/4 is indeed our slope. Okay, but they did give us a point, but it's not the y-intercept like they did earlier. It's a random point. So you know where this is headed. I know that I want my line to have a slope of 1/4, but it needs to pass through the point 8, 1. And my job is to write the slope-intercept form. We've done this before, and I've actually shown you 2 ways. You can either put it into point slope and then change it to slope-intercept, or you could put it directly into slope-intercept and solve for b. I like put it into point slope because it's a little bit faster. So I'm going to do y minus my y coordinate equals our slope, parentheses, x minus our x coordinate. And there I am already. So remember, point slope most often is just a jump-in point or jump in place. And then once I have my equation with my slope and my ordered pair where it goes, then I can distribute and move the 1, and I'm ready to rock and roll. So we'll distribute that 1/4 to the x, and also 1/4 times 8 happens to be 2. and then we'll move the 1 to the other side. So our equation would be y equals 1/4 x, there's our parallel slope, and then negative 2 plus 1 is a negative 1. This would be the equation of the line that is parallel to the one they gave us, but passes through the indicated point. So it's really, really important that you use that point in your new creation. You're not going to use that other equation for anything else other than to identify the slope of it so you can confirm that your slope will be parallel. That's the only thing you need it for. Okay? All right. Let's talk about some of the special cases because there's always some special cases, those Hoy vuxes. So, sketch a dotted line parallel to the x-axis and a solid line parallel to the y-axis on our graph. So, if we were to pick any location, but we just kind of created a parallel and a perpendicular parallel to each of these, they want a dotted line that is parallel to the x-axis. So maybe something like this. So essentially, if it's going to be parallel to the x-axis, it's going to have to be horizontal like the x-axis. And if I want to be parallel to the y-axis, then it's going to have to be vertical, just like the y-axis is vertical. Okay, so there's your two examples. And again, these are the special cases. So a line is parallel to the x-axis, or a line parallel to the x-axis will be horizontal. And it'll have a slope of 0. Remember, Hoy, the O is for 0. Okay. And then a line that is parallel to the y-axis will be vertical and will have an undefined slope. Okay, undefined slope. All right, let's just do a couple more here. Try number 8 here. It says determine the slope of a line that is parallel to the x-axis and passes through the point 0, -8. 6, -8. Then write the equation. So again, if we want to be parallel to the x-axis, that's like our dotted line over here, then it has to be horizontal. Horizontal, there you go. So it's got to be horizontal, and that means that the slope is going to be 0. However, we want this horizontal, remember, so this is a Hoy. Okay. Remember, Hoy is horizontal, has a 0 slope, and our equation will just be y equals the y coordinate. So our y coordinate in this case is -8, and so our equation would just be y equals -8. Because even though it's going to pass through the point, for example, 6, -8, the y coordinate will be -8 everywhere along that horizontal line. It'll be -8 all the way across. So sure, it'll pass through 6, -8, but the equation will be y equals -8 all the way across. Okay, let's jump down to number 10. On number 10, we're going to do this from a graph. Write the equation of a line that is parallel to the line H and it passes through 2, 3. So what we want to do is essentially what we did up there with the equation, but we're going to do it on our graph. We're going to determine the slope of this line so we can guarantee the same slope. And then we're going to also guarantee that it passes through 2, 3. So let's try it. What is the slope of this line? Let's pick a couple of good points that hit nicely and we can read. Definitely looks like this has a slope that is negative, and it is down 3 and forward 1. Down 3, forward 1. So we're looking at a slope of -3. -3 over 1 is just -3. But we want it to pass through this point. And so you could use your graph for this. I'm going to show you actually a couple of ways. So you've got a y coordinate of 3 we want to guarantee. We want to make sure it's parallel, and we want to make sure it passes through the x coordinate too. So I insert my x and y and my slope, and then I just distribute like we have been and move the 3. There it is. Okay, and so our equation is y equals negative 3x. That'll guarantee our perpendicularity. Our parallel, sorry. And then we have our 9. Okay. The other way you could have done this is once you knew what the slope was that you were interested in, you could have gone to the point 2, 3 and use that point to graph. So we come to our point 1, 2, 3, and we go down down 3 over 1, or up 3 and back 1. And when we graph that line, it's always nice to see it visually. There's a line, sure is parallel, and it passes through that y-intercept of 9, which is what we got over here algebraically, which is always really exciting to see our answers sort of confirm and support each other. Okay. All right, that is parallel line. So when you want to create a parallel line, you make sure your slope is the same, and then if they give you a specific location, you use that to write your equation. Okay, let's switch gears. You've already heard me say it a couple of times, probably not on purpose, but also perpendicular lines. So what does that mean? Quick review. So perpendicular lines are lines that intersect to form a 90-degree angle. Based on that definition, if we were to look at these and determine where that 90-degree angle is, you'd see anywhere where we have these boxes. So if we highlighted this out, this is a right angle right here. This side with this side. Or for example, in here, the height versus radius on a cone. These are all examples of 90-degree, right angles. You guys are familiar with those, etc. Okay. And here's kind of the cool thing about these. They also have a special relationship. They're definitely going to intersect. In fact, we see them intersecting here and here, here, here. Okay, but they're going to intersect in a special way. Okay, so if you look at this picture here, we're going to use this as our example. R, S, T, and U all intersect to form a rectangle, which means all of these are right angles, 90 degrees, if it's a rectangle. And if we think about this, which pairs of lines should have the same slope, right? Think about this. Two sides are going to be same slope because they're parallel, right? So if we look here, we know that the lines that have same slope means parallel, okay? And for that, we've got T and U. So T and U are definitely parallel to each other. And so are S and R. Also parallel to each other. These are symbols for parallel, by the way, so a little preview to geometry right there. Okay. Now let's compare. We already knew that it's a rectangle. So these are 90-degree angles, and then we know these are opposite sides are parallel. Let's go ahead and find these slopes. Take a moment and find the slopes of your lines, R, S, T, and U. Okay, and let's see how that went. So if you look at R, I look to see from this point to this point, we went down 3 and over 2. So this is a negative 3 over 2 slope for R. S, down 3 over 2, which we expected because we had already decided those were parallel. So that makes sense. Okay, but now take a look at T. So if you go from one point to the other here, and then reduce, you get up 2 over 3, up 2 over 3. So 2/3 here. And if you do the same with U, you also get that same slope, which again makes sense because we had already decided they were parallel. But more importantly, I want you to pay attention to the lines so the ones that were parallel had the same slope. We already knew that. The ones that are perpendicular, for example, R and T are perpendicular to each other. Look at their slopes. And I want you to pay attention to that relationship because this is at the root. Okay, so one example, R and T, for example, would be perpendicular. Another example might be U and S. Okay, and if you notice, this relationship right here, negative 3 over 2, positive 2/3, that is not a coincidence. That's actually a really important feature. It basically means we're doing the opposite sign and the reciprocal. Remember when we flip our fraction? And that's how you get perpendicular slopes. So for the ones that are perpendicular, the slopes are opposite, meaning opposite sign, and reciprocals. Not one, not the other, but both. Okay, so what that means is if one of them is A over B, as an example, then the other would be negative B over A. Okay, so you flip and switch is what I tell my kids. You flip it and you switch the sign. That's the real big idea here. So slopes of perpendicular lines are always opposite reciprocals. Write that in. And so to find it, all you have to do is flip the fraction and switch the sign. Flip and switch. Okay, flip the fraction and switch the sign. So let's practice that. We're going to wrap up with that. Find the slope of a line perpendicular to the given equation. So make sure y is isolated. Make sure that it's in slope-intercept so we can determine what the original slope was. If I want to be perpendicular, I don't want the same slope. That will give me parallel. I want opposite reciprocal. So I would take this 4 over 5. It's positive. So the first thing I would do is flip our fraction and switch the sign. Okay, that would be our new slope. If it looks like this guy right here, again, make sure that y is isolated. We've got negative 1/2. And so the opposite of a negative is a positive, and then we flip it. So that's 2 over 1 or just 2. If it's a whole number, remember when we talk about rise or run, if it's a whole number, it's really automatically over a 1. So that's our slope is positive 5 over 1 for number 3. Okay, so it's a positive, so I would change it to a negative, and I would flip. There it is. Okay. That would be our opposite reciprocal slope, and that would guarantee a perpendicular line. Okay, flip it over. We are going to wrap this up with talking about the special cases, and then we'll do a couple of these examples together. Okay, so if you look at the x and y axis, let's talk about those special lines one more time. A line, so if we were to create something, a dotted line that is perpendicular to the x-axis, so here's my x-axis, I want to be perpendicular to it. I want to make sure I hit it at a 90-degree angle. So that what would be perpendicular to this horizontal x-axis? Well, any vertical line. Okay, so a dotted line that is perpendicular to the x-axis might look something like this. This is just an example. And then a solid line that is perpendicular to our y-axis might look something like this. That would cross it at a 90-degree angle. Okay, so what do we observe? Horizontals and verticals, you probably already could tell that, are perpendicular to one another. So all perpendicular lines, or all lines perpendicular to the x-axis, are always going to be vertical, which means they have an undefined slope. And all lines perpendicular to the y-axis are going to be horizontal, which means they will have that zero slope. And that's important because the flip and switch is great, right? The one that we just talked about, where we flip the fraction and change the sign. But you can't really do that with zero and undefined. This is that, again, that exception, that special case where you just have to know that the reciprocal to an undefined is a 0, and the reciprocal to a 0, the perpendicular to a 0 is an undefined. So these are perpendicular to one another. Okay. All right, we'll try a couple of these. It'll be the same. We'll write the equation from the slope we're interested in this case, it'll be the opposite reciprocal, and the given point we want, and we'll be able to create our equation.